Hello, statisticians. We are learning about our last type of test that we're going to learn about in this unit, which is the t-test. So at this point, we have learned about just kind of what the whole idea of what hypothesis testing is. And then we focused on chi-squared testing, which has two different types of testing: a test for goodness of fit, of like following a certain type of distribution. And then our second one is a chi-squared test for independence, so to determine whether two variables are independent or not. So those are the two types of tests we've learned so far. And the t-test is a test that we calculate to test if the mean has changed from a previously known value. In other words, we're just kind of comparing averages. It's very applicable, very usable. You'll see all the real world applications of why we would carry through this test in our problems below. But we definitely use this a lot in the real world. If you watch Mythbusters, like this is how Mythbusters makes their final determinations of gathering all of their data, and then they calculate a t-test, and the t-test will determine whether or not that there's statistically enough evidence or significant evidence to show that this isn't just happening by chance, that there's actually like something else driving this forward. There are a few things to know about this test. Mostly, my biggest thing is that it's only used for normal distributions. And that's one of those caveats that we have to like know is true in order to use the t-test. We have to know that it follows a normal distribution in order to be able to use the t-test. So that's a big part of statistics in most statistics classes, that you have to like determine whether or not you have enough information or have the right type of information to be able to follow through with this t-test. In this class, that's not really going to be the point of these types of problems. For the most part, I think I will reserve the right to amend that statement at a later date. For the most part, you will be told, calculate the t-test, calculate the chi-square test. You won't need to be able to cipher through the information and determine whether or not you have the right information in order to be able to follow the calculations. But you might see, if you're like doing some practices online by yourself, you might see that that's the type of question of like, hey, do we have enough information to be able to go through with this test? And normally we're looking for a normal distribution. That goes along with this idea that the two data sets that you're comparing their means for, they need to have the same variance. They need to have the same type of spread. And that goes along with the normal distribution aspect. Normally, if you're comparing things like two different schools, or if you're comparing things like two different healing gels on the same type of cut, they're following along. You're comparing things that should be compared, right? If they have completely different variances, then they're two different things that are being used on two different ends of a spectrum, potentially. So the idea of having the same variance is you're like, hey, we should be using similar things on a similar situation, and that will show us some evidence about what we're comparing. Hopefully that makes sense. Okay, a common example of t-tests are when we're testing for a new treatment for medical conditions. Suppose you want to determine if a new antibiotic cream will heal a cut faster than the existing treatment will. We will give the first group of people the new cream and count how many days it takes for a cut to heal, which gives us mu1, our first average. And we gather another group of people, give them the old cream, and count how many days it takes for their cut to heal, which will be mu2. Since we are dealing with two different groups of people, we can assume that the sets are independent. So they do need to be independent as well. In addition, we want to know if the new cream works faster, so we would complete a one-tailed test with the following hypotheses. So let's go ahead and list out our hypotheses. Your null hypothesis for all of these problems are always assuming that the old value stays the same. So your null is always that the average stayed the same. So with all of these guys, kind of like with your chi-squared null hypothesis, where the null hypothesis for independence is always they are independent, your null here is that they are the same. The two averages are the same. Alternatively, your alternative hypothesis determines whether or not it's a one-tailed or a two-tailed statistic. So we've talked about this in our very first lesson of this unit. It tells us that it's a one-tailed here, which means it's either going to be greater than or less than. So we need to determine which one of those it's going to be. And it says we want to know if the new cream works faster. And if these averages are time it takes to heal, then if a cream works faster, then the time it takes to heal would be less than. It can be really confusing, very trippy, very tricky. So just watch out for that. So I'll say it again. If we're testing to see if this guy worked faster than this guy, then that means that our new cream would have a less time than our old cream. So we're saying, hey, okay, well, if they're not equal, then they're definitely, the new cream is going to have a smaller average than the old cream. So your null hypothesis is always that the averages are equal. And then the alternative hypothesis from that is going to be either you need to determine whether it's a one-tailed or a two-tailed. And so if there's any indication of like, okay, well, we are assuming that it's going to, or we're predicting that it's going to be faster, or we're predicting or hoping that the averages are going to be greater. That type of wording in the problem is going to indicate to you what your alternative hypothesis should be and whether it's going to be one-tailed or two-tailed. If it doesn't say like, oh, we're predicting it's going to be greater, or we're testing to see if it's going to be less than, and we're just saying, hey, we're comparing averages, and there's no indication of greater than or less than anywhere in the wording of the problem, then your alternative hypothesis would just be that they are not equal, and we'll see that in a later problem. Okay, now that we have the type of test to run, let's consider the data for the two groups and perform a hypothesis test to determine if the new cream decreased in the healing time of a cut with a 0.5 significance level. So we have our data. We're going to grab our handy dandy calculator on. Let me erase some statistics I was doing on here. So we are on our spreadsheets list, and we just need to input our data here into the calculator. Almost always your data will be given to you such that this first row goes into the first column, but I always like to just take a second and double check that my mu1 is the corresponding first column, and mu1 deals with the new cream, and so that one should go into the first column. It's not something you should really worry about. It'll be typically presented to you in a way that that you would do that anyway, right? So it's not something that you need to worry about, but it would be a potential way for the for a test to try and trick you and double check, hey, do you know what you're actually talking about here? But I don't think it's going to happen. So we just want to make sure that our mu1 data is here and our mu2 data is there. Okay. Now that we've entered in our data, we're going to hit menu. We're going to go to statistics. And instead of stat calculations, we're going to do stat tests like we did with our chi-squared. And now we're going to talk about a t-test. And t-tests aren't really grouped like chi-squared was. You can see a t-test right here. That's not what we're doing. We're doing a two-sample t-test. We will always be doing a two-sample t-test. Realize that you can grab data from a bunch of different situations, and you can bring in like multiple different data sets into a test. And that's why there's other options for t-tests, but we will always just have two sets of data that we're comparing. So we're always going to do our two-sample t-test. Our input method will change, but in this situation, we're just putting in data. So that's why we say data here, is that we've just put in raw data into our calculations. So we press enter on that. And then we get this. List 1 is your mu1, and we put that into A. List 2 is mu2, we put that into B. Frequency of all of those guys is 1. Alternative hypothesis. We have never had to talk about what our alternative hypothesis is, but it's important here because we're talking about, are we doing a one-tailed test or a two-tailed test? And your mathematics behind it, the mathematics that are programmed into your calculator, change. So we do need to tell them the appropriate alternative hypothesis, which is that mu1 is less than mu2. I just clicked sideways here to be able to get my options. So then I'm going to scroll down to say mu1 is equal to mu2 and press enter. Another thing that we have to make sure to change is pooled. It will always be a pooled test, always. You don't even need to worry about what a non-pooled test is. So just don't worry about it. Results going into column C, don't worry about shading or anything like that. We press enter and here we go. We get a t-value, which you see right here, but we are always going to be focusing on the p-value with our t-test. So hopefully, if you haven't already, definitely rewind this video and write down the set of instructions, what buttons you press. If you got a TI-84, Cognidy is your best option in terms of like finding instructions for a TI-84, or you can just type into YouTube and say how to calculate a two-sample t-test on a TI-84. And you've got a bunch of people out there who want to help you and show you how to do it. Okay, p-value is 0.04512. And now we need to compare that to our significance level. So we have our alternative and null hypothesis. We plugged our data into the calculator. We grabbed our p-value. Now we need to compare the p-value to our significance level. Since 0.0452 is less than 0.05, remember you can always add on as many zeros as you want to determine, hey, which one of those numbers is bigger. Since we know that our p-value is less than our significance level, we have enough information to reject our null hypothesis. So we say that since our p-value is less than the significance level, we have enough information or data to reject null hypothesis. This means that we can conclude that the average time to heal for our new cream is less than the old cream. So when you see that like people have done tests and they're saying like, oh, well, we've concluded that like this statistically, we've concluded that there's a significant data to be able to say that this new cream is better than the old cream. This is the process that they go through, is that they say, okay, we're going to gather data. We're going to do so many sets of data. We're going to gather that information. We're going to create a t-test based off of that information. We're going to compare it to a certain significance level, like 0.5. 0.05 significance level.